If we seriously want to become a truly advanced civilization, building a Dyson sphere around the Sun will be only the first step. A bit later, we'll colonize the entire Milky Way by constructing a transport network around it. Then, we'll travel to other galaxies and turn the whole universe into our backyard. These are the measures humankind needs to take to move up the famous Kardashev scale, and each stage will require more energy and remarkable technological breakthroughs. However, all of this won't matter, and our expansion will never become a reality unless we fulfill one vital condition. To have at least a slim chance of getting beyond Earth, we'll have to tame the mysterious force that affects both you and the whole universe at this very moment. Despite its influence, scientists have no idea what it really is. The name of this phenomenon? Gravity. It sounds unbelievable, but the moment we start uncovering its secrets, we'll begin climbing the Kardashev scale without any effort. But how exactly will gravity help us conquer the universe and move beyond? Just imagine you start your day with a tour around the giant Dyson sphere that encompasses the Sun. A few hours later, you have lunch on a space station overlooking Mars. In the evening, you go ice fishing with your friends on Europa, Jupiter's moon. It's a dream scenario for us and a typical weekend for a citizen representing a Type 2 civilization on the Kardashev scale. Well, at least we've already started moving towards such a future, and studying gravity is our main stimulus here. The first person to cast some light on this natural force was Sir Isaac Newton. It doesn't matter whether an apple fell on his head or not. What's really important is his famous research, published in 1687, that brought the world the law of universal gravitation. That was a brilliant insight, but it created an unsolvable paradox. Earth not only attracts objects on the surface, but it also pulls on the Moon, the Sun, and distant planets, even though its influence isn't strong. But how does it travel in the emptiness of space? Newton himself openly called this property of gravitation so great in absurdity that it's better not to think about it at all. Nevertheless, his formula worked just perfectly. With its help, in 1846, French astronomer Urbain Le Verrier analyzed oddities in the orbit of Uranus and calculated the orbit of the planet that was yet to be discovered, Neptune. His calculations were amazingly correct. However, in the late 19th century, it was established that the long-known celestial body named Mercury flatly refused to follow Newton's law of gravitation, as its orbit pulls some weird and incredible tricks. It seemed that gravity itself functions very differently near the Sun. Albert Einstein was the first scientist who dared to say, yes, it really does. According to his theory of relativity, gravity isn't a force, but the result of space-time fabric getting curved around objects. Unlike other planets, Mercury ended up in a deep part of the Sun's gravity well. That's why its orbit is so bizarre. This discovery made Einstein's theory of general relativity the leading theory about gravity. It helped NASA send a human to the Moon and work out the details of gravity assist, which let the Voyager probes go to the most distant planets of our solar system. But sometimes, even this classical mathematics brings surprises. In 1990, NASA engineers noticed that the two probes launched before the Voyagers, Pioneer 10 and Pioneer 11, started both slowing down as they approached the outskirts of the solar system, as if something was pulling them back in. In the two following decades, scientists proposed a lot of theories, from trivial gas leaks to the impact of invisible dark matter, but none of them fully solved the Pioneer anomaly. It looks like, far away from the Sun, its gravity well is deeper than we thought. Moreover, even super-powerful computers at NASA's disposal are still unable to finally crack the unsolvable three-body problem, or how to predict how three objects mutually attracted by gravity will move. So far, only astronomers care about these enigmas. But if we're seriously interested in becoming a Type 2 civilization on the Kardashev scale, we'll have to substantially modify our mathematical approach to gravity. A Dyson sphere or a Dyson swarm consists of various interconnected satellites with solar panels, supposed to shroud the Sun and maneuver to keep their balance when attacked by the star's violent wind, and all of this while staying in the deepest area of the gravity well. If we make even the slightest error in calculations, our space generator will fall to pieces before we finish its production. But super-accurate predictions of gravitational effects will be crucial for our future Type 2 civilization all around the rest of the solar system. Back in 2002, Martin Lowe, a mathematician and spacecraft trajectory expert from NASA's Jet Propulsion Laboratory, came up with a bold concept called the interplanetary superhighway. It's essentially an unstable network of gravitationally determined pathways between planets and satellites of a solar system. This will not only allow us to save fuel used by spacecraft, but also considerably reduce the duration of their trips. Actually, the Voyagers make use of this effect, but compared to the interplanetary superhighway's true potential, their flight was like a bike tour along the roadside. We must learn how to benefit from the gravitational effects across the whole solar system in real time, and only then we'll be able to visit Mars at lunchtime and have dinner on Europa. But even the most perfect math formulas aren't enough to take a step toward other stars and beyond. As a member of a Type 3 civilization on the Kardashev scale, you'll be able to go on vacation to any of the paradise planets registered in the Milky Way and immediately post photos of your adventures via the intergalactic internet, all thanks to uncharted gravitational effects we're just beginning to figure out. While the general relativity theory's predictions about the nature of gravity came true on a cosmic scale, they caused new paradoxes on another level of the universe. Any regular electron found in any atom has a tiny mass. However, according to Einstein, even this mass should faintly warp space-time. On top of that, the electron's extremely high energy of motion would lead to more noticeable ripples in the fabric of space, which in turn would make the particle even more charged, and that would mean further warping. As a result, in split seconds, you have a mini-nuclear explosion that occurs in every molecule of the universe. Bright minds such as Erwin Schrödinger, Paul Dirac, and even Robert Oppenheimer, the father of the atomic bomb, spent decades trying to combine Einstein's perception of gravity and quantum mechanics and ran into impossible infinite numbers over and over again. Any scientist would conclude that a dead end like this is a sure sign that the theory is flawed, but Einstein didn't go into hiding and was ready to strike back. In 1935, he and his two co-authors pointed out that quantum mechanics also produces an inexplicable phenomenon. Quantum entanglement means you can create connected particles and put them very far away from each other. Then, after you evaluate the state of one of them, you can make one particle immediately reflect the state of its companion. In addition, this communication can overcome any distance and happen within an instant, in fact, infinitely fast. Einstein thought the speed of light was the highest possible, so to him, the discovery meant that quantum mechanics was misleading, even though quantum entanglement turned out to be absolutely real. Yet opponents of the theory of relativity soon found another infinity there, and this time on its home ground, in space. A powerful gravitational field around a black hole comes from a mysterious object located in its center, a singularity. According to formulas, it's incredibly massive and at the same time infinitely small and infinitely dense. To get rid of this paradox, in 1935, Einstein published another scientific paper that described a pretty exotic curvature of spacetime. That was a wormhole, some sort of funnel-like tunnel in spacetime connecting two black holes across any distance. This idea removed the infinities, although it was impossible to prove the existence of these tunnels in practice. Moreover, subsequent mathematical calculations showed that wormholes would collapse under even minor gravitational perturbation, not to mention attempts to send something through them. Thus, together with the hope to resolve gravity paradoxes, we waved goodbye to our dream of instantaneous space trips. Or am I wrong? In 2013, physicists Leonard Susskind and Juan Maldacena took a fresh look at the long-standing feud between quantum mechanics and the theory of relativity and came to an unexpected conclusion. They asked, what if the nature of wormholes is no different from the nature of quantum entanglement? Simply put, in both cases, unknown gravitational effects act as connection providers that keep working at any distance. In 2022, a research team headed by Maria Spyrapoulou used the most powerful Sycamore quantum processor to carry out a bold experiment to test the theory proposed by Susskind and Maldacena. Using entangled qubits, the scientists tried to create a mathematical replica of an object that would combine properties of both a wormhole trap between black holes and quantum entangled particles. The team named it a holographic wormhole. Although, in fact, this was an advanced digital simulation. Quite soon, physicists not only finished developing this mythical thing but also sent a particle through the virtual spacetime tunnel without destroying it. In other words, if wormholes and quantum entanglement are indeed the same things, this makes Einstein wrong and faster-than-light travel possible. Wormholes will be a basic necessity for a Type 3 civilization on the Kardashev scale to keep in touch and move around the galaxy within reasonable periods. But even this will be just a prelude to the breathtaking opportunities that will open up for us together with the deepest mysteries of gravity. If you're a member of a Type 4 civilization on the Kardashev scale, you don't need any wormholes to cross giant abysses that occupy millions of light-years between galaxies. And when you get bored with trouble-free traveling, you can watch the Big Bang or even the very end of the universe because its time and space are entirely in your hands. This can be achieved, that's right, by delving deeper into the nature of gravity. The first advantage it'll bring will be a highly detailed map of the universe. In 2022, scientists from Johns Hopkins University presented a 3D map of a broad segment of the night sky covering more than 200,000 galaxies. Not bad for a start. But take your time planning colonization roads. The map of the universe is different from what it seems. Distances on the map are measured not only in spatial but also in temporal dimensions. In other words, when we look at a galaxy located a billion light-years away, we see it the way it was a billion years ago. And even if a Type 3 civilization manages to discover an ultra-distant wormhole to that space region, it'll end up in the middle of nowhere since our universe expands exponentially. The destination galaxy may turn out to be millions of light-years away in a completely different direction. Unfortunately, on the scale of space, the speed of light is too low to seriously rely on telescope observations when it comes to really long journeys. In addition, apart from speed, light in our universe has another fundamental limit. On the 3D map released by Johns Hopkins University, this limit is indicated by the upper border. This is the cosmic microwave background, or the first light that traveled through the universe. It was emitted by primordial atoms of hydrogen approximately 379,000 years after the Big Bang. But if we want to create the most accurate up-to-date map of the universe, we need to look into the past much further, as close to the Big Bang as we can possibly get. We can do it with the help of gravity. At the turn of the 21st century, scientists working for LIGO set themselves the ambitious task of finding something nobody had ever seen before: gravitational waves. Einstein predicted that any interacting objects with mass would produce barely visible ripples in the space-time fabric, spreading around the universe. LIGO needed 13 years to detect gravitational waves. It finally happened on September 14, 2015, after a collision of two massive black holes. Since then, LIGO has spotted this faint glow from dozens of times as it came with other similar collisions. Most of it remains invisible to regular telescopes because gravitational ripples can go through any obstacle in space, including that impenetrable wall of cosmic microwave background. Right now, the whole universe is filled with gravitational wave background that keeps the memory of all interactions of matter starting from the very first milliseconds after the Big Bang and even the Big Bang itself. In collaboration with the European Space Agency, NASA is developing the LISA space mission and hoping that the device's laser detectors will manage to at least partly observe the elusive gravitational wave background. If we obtain this information, we'll be able to create the most complete chronological map of the universe and be sure that our descendants from a Type 4 civilization will never get lost trying to reach faraway galaxies. But wait, how exactly will they get there anyway? This red blob is one of the most remote galaxies photographed by the James Webb Space Telescope. Astronomers assume that the real distance to that place is greater than 33 billion light-years, meaning that we don't stand a chance of visiting it. Don't forget that the universe expands exponentially, so the galaxy drifts farther away from us several times faster than the speed of light. By the time we master the technology for creating wormholes, it'll be too late since billions of galaxies will forever disappear beyond the cosmological horizon. Unless we invent the gravity-based time machine. Einstein claimed that black holes severely warp not only space around themselves, but time as well. Their impact is so significant that time turns into loops connecting the future of black holes with their own past. Therefore, following a certain trajectory near the event horizon, you can jump to any point of time you want, even travel billions of years back. It's easy to imagine a fleet of spaceships operated by a Type 3 civilization that uses gravity maps and scatters around the centers of neighboring galaxies. The ships find supermassive black holes, and through them, they travel to the early universe before it started expanding. If this comes true, we'll get a chance to colonize even the most inaccessible corners of space together with our distant future and past. Who knows, maybe when we look at that red blob, we actually see a galaxy already populated by our distant descendants. But who said they'll be satisfied with just one universe? Close your eyes and imagine that your power of thought is enough to take you to hidden dimensions and let you surf through the endless multiverse. I'll tell you more, you can even create new worlds at the snap of your fingers. Some people might call you a god, but no, you're a member of a Type 5 civilization on the Kardashev scale. So how does this trivial force of gravity work in the shadow of your almightiness? If the four fundamental interactions of our universe were superheroes, their power levels would be much more uneven than those of the Avengers. The power of electromagnetism would equal 1 followed by 36 zeros. That's way more impressive than what Thor, the god of thunder, can do. However, the character able to control the strong interaction would be 100 times more unstoppable. Even though the female superhero controlling the weak interaction would be trillions of times less influential. And compared to her, Miss Gravity wouldn't even be the teen's Black Widow. That's because on the general background, the indicator of her force equals 1, and I mean just 1, without any zeros after it at all. This is more than the discrepancy between the diameter of a single atom and the entire observable universe. Gravity is so weak that this morning you already defeated the whole planet's pull by just rising to your feet. Scientists have been racking their brains over the hierarchy problem of physical forces for many years, and some of the solutions may give us access to another side of the universe. Most physicists view our world as a three-dimensional space with an additional fourth dimension, time. But not genius mathematician Edward Witten. He dedicated his career to developing the so-called M theory. It doesn't use poles and particles to explain all physical interactions, but refers to vibrations of tiny strings instead to describe the diversity of the universe. This way, Witten needed 7 new spatial dimensions. When asked where exactly we can find them, he and his followers come up with different answers. These dimensions are either compressed into tiny wormholes at the subatomic level or exist just like our 3, but on the inside of the universe. That reminds me of the Upside Down from Stranger Things. And although the whole thing sounds so unrealistic, the mathematics of M theory works perfectly fine with 11 dimensions. But most importantly, gravity in this multi-layered universe appears by itself. Besides, it's very weak since it has to break through 7 additional dimensions to reach our 3-dimensional space. So according to Witten, gravity is like a droplet that leaks from the ceiling during heavy rainfall. Unfortunately, right now there's no way to test M theory and probe all those new dimensions where gravity originates from. But physicists that'll be part of Type 3 and Type 4 civilizations will definitely succeed in this, and perhaps they'll also discover that the true nature of gravity is even more complicated. Right now cosmologists are trying to crack an unsolvable mystery: where is 85% of the total mass of the universe? This substance is known as dark matter, although scientists have no idea what it is. All attempts to find previously unidentified particles failed miserably. But what if we're looking in the wrong place? This exact question prompted desperate physicists to create the concept of a hidden valley, meaning a whole separate universe that's parallel and adjacent to our own. It produces all visible gravitational effects. Some researchers go even further and describe the multiverse, where bubbles of adjacent worlds have radically different laws of physics and attract each other with the help of universal all-pervading gravity. One way or another, now we're just grasping at straws, hopeful to explain the paradoxes of this natural force. But so far, all these theories don't tally. And yet, no matter what the true nature of the weakest and most important fundamental force turns out to be, there's no doubt it'll be the key to our future supremacy and omnipresence. I have one last question: how exactly will gravity help our descendants create new universes? Oddly enough, this one is the easiest to answer. In 2021, Canadian cosmologist Robert Brandenberger suggested a surprisingly simple idea to explain infinitely dense singularities inside of black holes that annoys everyone so much. According to him, There's no wormhole opening in this extreme point of space-time. Instead, another Big Bang is happening there and a new universe is forming. If this is true, and the civilization of the future learns how to make gravity wells like those near black holes, it'll amount to the divine power of creation. There is another option, though. Futurist John Smart believes that our descendants will be using extremely powerful quantum supercomputers to unravel the mysteries of outer space. As soon as they optimize their design and performance, these machines will look exactly like black holes. With a supercomputer like this, we'll be able to simulate entire universes without leaving our houses and sitting on the couch next to the Dyson sphere. But what if everything has already happened, and right now we live in a simulation of the universe created by human generations of the distant future? Maybe they're very nostalgic about the good old days when paradoxes of gravity and other world mysteries seemed unsolvable. And perhaps with our help, they want to feel the joy of making exciting discoveries once again. So if one day you manage to hack into the Matrix and access knowledge those in charge of the simulation possessed, don't forget to let everyone know and leave a comment. There are so many questions buzzing in my head.